Let's apply what we just learned to a data set about Wall Street executives and the perceptions Americans have. So suppose you're a financial analyst and you want to test this hypothesis that the proportion of Americans who think Wall Street executives are greedy is evenly split. So you collect data from a random sample of adults living in the United States and you ask them several questions on their views of Wall Street executives. This is what the data set looks like. This is a real data set. It's a random sample of 810 US adults. So we can see that we've truncated part of the output, but you can see the top and the bottom of this data set. And we have several characteristics of the respondents, including all these questions about what people think of Wall Street executives. So in this case, we're interested in what Americans think about Wall Street executives in terms of are they greedy or not. So let's do a point estimate of the proportion. We'll call P equals yes and 1 minus P as no. Right, so that's how we define the success and failure. And in this case, yes means people think that Wall Street executives are greedy. No means people think they are not greedy. So the point estimate p hat we can just calculate using a basic tabulation. So we find that 17% of Americans think Wall Street executives are not greedy, and we think about 83% of Americans think Wall Street executives are greedy. This is from a random sample of data. So our value of p hat is 0.83. Now the thing is that this is a random sample. Maybe just through sampling variability, we have this sort of extreme value of p hat. And maybe perhaps in the population, p is closer to 0.5. So we want to make an inference, and we want to test a claim about p. So first of all, let's check the success-failure condition. Again, this is a claim. This is sort of a condition about the population, but we can use p hat as an estimate of p to assess or check this condition. So the success-failure condition says that p hat will be approximately normally distributed on the sampling distribution if n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10. So plugging in p hat for p and using our sample size at 810, we'd expect the number of successes to be about 672, and we'd expect the number of failures in that sample of 810 to be about 137, 138. Both of these values are greater than 10. The expected number of successes and the expected number of failures are both greater than 10, so we can be quite confident that the sampling distribution for the sample proportion p hat will be approximately normally distributed based on this sample size and based on this value of p hat for that population proportion p. So we're going to go ahead and conduct a one sample z test, which is based on the standard normal model of the sampling distribution. So for steps 1 and 2, we want to first outline our hypotheses and state our significance level alpha. So we're conducting a two-sided z-test, and we have the following hypotheses. Right? The claimed value for the population proportion is 0.5. Right? The claim is that Americans are evenly split. Roughly half think that Wall Street executives are greedy, the other half think they are not greedy. So that's the claim we're testing about the population. You're a financial analyst, the executives that you work with think that Americans are evenly split. The alternative is that the population proportion is not equal to 0.5. Either the population proportion is greater than 0.5 or it's less than 0.5. But the point is that Americans are not evenly split. That's the alternative hypothesis. So we're going to set alpha to 0.05. So our critical value for a two-sided test is going to be 1.96. For step 3, we calculate the z-test statistic. So for sample proportion, right, z is p hat, or sample proportion, minus the claimed value of the null divided by the standard error, where the standard error is essentially sigma divided by square root of n. We just calculate it in a slightly different way because we're dealing with proportions and it's more convenient to calculate it that way. So since p hat equals 0.83 and the claimed value of the proportion of the population is 0.5, that's what we're testing, and the sample size is 810, we can calculate a standard error of 0.0176. This is sort of the expected standard error. This is the expected standard deviation of that sampling distribution. So based on this standard error, we can calculate a z-test statistic of 18.75. Right? Again, this is the z-test statistic. We compare that to the standard normal distribution. So with the z-test statistic of 18.75, you should already have an idea at this point that that's a pretty extreme test statistic. So let's actually compare this test statistic with some critical value and then calculate a p-value using this test statistic. So we're conducting a two-sided test. So the critical value, all right, is going to be based on this value of, if our absolute value of the z-test statistic is greater than z alpha divided by 2, then we're going to reject the null, that the population proportion is 0.5, that Americans are evenly split. So since we're set alpha to 0.05, alpha determines our critical value, and that critical value is 1.96. So the absolute value of our z-test statistic is 18.25. That's greater than 1.96, so we reject the null that the population proportion is 0.5 at the alpha 0.05 level. We can also calculate a p-value, a probability value. So for a two-sided test in which the population proportion does not equal the claimed value of the population proportion under the null as the alternative, the p-value is simply the probability of obtaining a z-test statistic greater than or equal to the one we obtained in absolute value multiplied by 2. We multiply by 2 because we're interested in extreme test statistics that are very positive or extreme test statistics that are extremely negative. In our case, the p-value is very close to 0, and we can visualize this. So here we have a visualization. That distribution off to the end, that is where the sampling distribution should be located if that null is true. If the population proportion is actually 0.5, that's where the sampling distribution should be located, and that's roughly the shape that we'd expect it to have. Our sample of data is located way off on the end. That's because that reflects the z-test statistic, that's 18.25, and what it's reflecting is that if that null is true, it is really unlikely that we would have obtained a population proportion of, or a sample proportion of, that we in fact obtained, right? To put another way, if the population proportion is 0.5, it's really unlikely, given what we expect to find about the sampling distribution, it's really unlikely to actually have a sample proportion of 0.83 just through random sampling variability. So this suggests we're going to reject the null because the probability of obtaining a test statistic as more extreme than the one we obtained is pretty much 0. So we reject the null by comparing our p-value, which is very close to 0, to our alpha level of 0.05. At this point, we can make a conclusion. So we're going to reject the null that the proportion of the population is 0.5 at the alpha equals 0.05 level. To put another way, right, Americans are not evenly split on their opinion of Wall Street executives. The overwhelming consensus is that Wall Street executives are, in fact, greedy. I also recommend that we calculate a confidence interval. So a 1 minus alpha times 100% confidence interval for the population proportion can be calculated by taking p hat plus or minus z alpha divided by 2 times the standard error. So we're going to use p hat now as an estimate for p when we calculate the standard error, and the 95% confidence interval is simply 0.796 to 0.864. So we're 95% confident that the true proportion of the population is somewhere in that interval. So it's, in the 80s roughly, roughly 79.6% to 86.4%. We're 95% confident that the true proportion in the population lies in that interval. And with that, we've completed our first example dealing with a test for a one-sample proportion.